so we're happy to have Patrick for the next talk.
Thank you. So I'm going to be talking about a systematic bottom-up approach for classifying scalar EFTs. Most of this talk is based on these references. First one is sort of a large, comprehensive paper which came out end of last year by these authors, and it really builds on techniques that were developed in these two papers, which came previously. And so paper 2 sort of uses soft limits and some techniques we're going to encounter to explore effective field theories, and they actually find a novel effective field theory which no one knew about before. And you have interesting numerical procedures, but we're going to not have time to talk about that. We might get to talk about the methods of paper reference 3 a little bit, which of course are incorporated in 1. And so we'll see how that goes. So the outline, I think I'm going to kind of mix things up because I'm going to sort of say what we're doing and why and try to motivate some of this, and then go over the approach. And then I want to get to the results because I don't want to leave those to the end where it might get time crunched. And then once I outline the results, I'll just sketch them. Then I'll show you as many methods as we can get through for how we do this. OK, so what is the goal? The goal is to systematically explore space of scalar EFTs consistent with Lorentz invariance and a local S matrix. OK, so why scalar EFTs? They're the simplest. We got to start there. And then we just take basic physical considerations is what we're doing. The authors of these papers have, I think, a background in doing work in the amplitudes program, and these techniques grew out of that. So the goal of the amplitudes program is, of course, to construct the S matrix without the aid of a Lagrangian, which has both pitfalls and benefits. But one of the benefits is that there's an infinite class of Lagrangians which correspond to the same theory. And they're all related by field redefinitions, and integration by parts identities, and even some kinematical considerations. And it can be a real pain to identify, know which Lagrangian is giving you a unique theory. We saw in class even enumerating higher dimension operators for the standard model is quite a non-trivial task. So if you just get rid of a Lagrangian, you construct the scattering amplitudes directly, you know by examining their properties if you found a unique theory. So much of this has been done with Yang-Mills theory and gravity with a lot of success. But not so much with effective field theory. So that's what these people are doing. And we hope to develop techniques which will allow us to use symmetry with these amplitudes to discover theories. So when you have a Lagrangian, it's very easy to impose symmetry. It's very manifest. But it's not so easy to do with just directly with amplitudes. OK, so what is like a physical the canonical example of symmetry and amplitudes? It's something called the Adler zero. So this basically states that if you take the soft limit of a certain amplitude, it will be 0. And what kind of amplitude is this? In the original context, it was an amplitude for pion scattering. So this p corresponded to a pion line. And it was because of the spontaneous symmetry breaking, which gave you your effective theory. There's a residual symmetry hidden in the amplitudes, which causes this to happen. So when this is a Goldstone boson, this holds. And this is a general feature. So what this has been known since the 60s. What these authors did was they said, OK, perhaps we can use something like a generalized Adler zero to constrain our effective field theories. So if we say our amplitudes in some soft limit vanish according to some power of the momenta, this might be enough, along with Lorentz invariance and the locality, to constrain the theory and produce some things we can work with. So that's sort of what was developed in reference 2. So this leads to a method for classifying these, or labeling these theories, which I'll just introduce because we're going to work with it quite a bit. Let's see. So each theory is labeled by a tuple of numbers. All right, rho, sigma, v, and d. So let me write down what these are. Rho is roughly number of derivatives per field. Sigma, degree of vanishing in the soft limit. V is the valency of leading interaction. Valency just meaning how many fields are interacting. And D is the dimension, space-time dimension. So rho is a positive rational number. The rest are positive integers. And so we're going to take a bottom-up approach where we declare a tuple of these numbers. When we declare a tuple of these numbers, we're going to search if we're going to try to find a theory which could exist with those parameters. So this is again different from the sort of top-down approach of you declare Lagrangian, you compute your Feynman diagrams, you check what's going on. And that's totally possible and straightforward, but it's just very unwieldy. Okay. So now, sort of having gone over this tuple, I'm going to sketch the results. So I'm going to make this fancy plot. Where, of course, we can't show the whole four-dimensional space here, but this is sort of the most useful projection. Here. So, turns out that this whole region has trivial soft behavior. So so sigma again is the vanishing of the amplitude in the soft limit, and it's trivial that an amplitude will vanish with at least the power according to how many powers of momenta it has. So this line, the line basically, it's not very straight, but rho equals sigma, that's the line where you expect everything above here is just automatic from counting the numbers of powers of momenta. And theories can live here, but we're not going to consider these theories because you don't get constraints from anything like a generalized Adler zero. So we're going to really focus on theories which are below this line, and then the authors of these papers argue that these theories are sort of special and they're in some sense analogous to Yang-Mills and gravity because you can basically construct them entirely in terms of these simple principles. They're sort of one or maybe sometimes two parameter theories. So we have this whole region is ruled out. All over here. This is ruled out. So this is trivial. This is impossible. And this just continues. And then this is sort of the region where we find theories existing. And we can sort of place some of the theories you may be familiar with. So the nonlinear sigma model lives here. The details of what these are won't be important. Something called PX theory, which the authors define, lives here. There's a Wess-Zumino-Witten part. I think it's a term in the nonlinear sigma model. It's living somewhere here, depending on V and D. There's the DBI, or Dirac-Born-Infeld theory, which is coming from some considerations of D-branes and who knows what. There's the Galileon theory, which lives here. And again, the details of what these are don't really matter. They're just theories which you might be interested in. And then, sort of interestingly, what was found in reference to was an entirely new theory living here, which they termed the special Galileon. So I'll write it Sgal, which apparently no one knew about, and it has a hidden symmetry, which allows it to have this amount of vanishing. If you sort of think about it physically, how is it that you can have an amplitude which vanishes faster than the powers of momenta that's just corresponding for each field? And what's going on there is there's non-trivial cancellations happening in the amplitude between contact terms, contact diagrams, and different tree structure diagrams. This is all at tree level, I should mention. So, so you may think like this is why isn't this like dependent on d for some dimension, or why isn't this scale with how large the theory is? It's because having a large sigma value really means you're like have extremely non-trivial cancellations happening, and at some point, as we'll find, by some of these methods, just it's impossible. It's over-constrained down here. You can't have a consistent theory down here. Okay, these theories on this line are called the exceptional theories because they saturate this impossibility bound, and those are sort of the ones that the authors argue are analogous to gravity and Yang-Mills. Okay, let's move on to. Well, let me just write down really quickly so you have sort of in your mind what a Lagrangian might look like for these sort of theories. Schematically, we might have something like will be to infinity. So here we see the valency appearing. Might look something like this, where this is, of course, ignoring all Lorentz structure, but for a given, so these coupling constants, there's actually can be many of them at a given m and n level. There are many different ways to Lorentz contract these different fields, but this is just schematically, and that sort of gets at why it's very difficult to enumerate all possible Lagrangians. So if you had a rho equals this, this is the valency again. It starts the minimum amount of fields which come together at any point. An example would be like. Rho equals, I should define rho, first of all. Rho is defined to be m minus 2 over n minus 2. They put the minus 2 there because they factor out like a kinetic kind of piece. And they're considering only derivatively coupled theories here. So rho equals 0. This looks something like this, and in I think in reference 2, the authors show how cancellations can occur only between terms of a fixed row. So in all of that's we're going to discuss here, we're only going to consider theories of fixed row. You can of course have theories of mixed row, but you only need to sort of analyze and understand ones at a single value of row. Okay. Okay. All right, now we should sort of proceed with some of our methods. So we're going to take an ansatz for what an amplitude in any of these theories could look like. And that's going to be of the following form. Okay, where these Sij are kinematic invariants corresponding to. So general amplitude parameterized by n and m, function of these kinematic invariants is the sum over topologies, different tree structures that you can form of some numerator over some denominator, and then there's this contact piece, which is where there's no internal propagators, so it's just a single interaction. So this is some polynomial momenta, this is some rational functioning momenta. And a couple details here, we can in a derivatively coupled theory of scalars, you can always make a field redefinition to remove a cubic vertex. So our minimum v we'll consider is v greater than or equal to 4. Okay, So this amplitude must factorize if one of the internal propagators becomes on shell. So in that limit, we have this, where this momenta is like the sum of everything on the left-hand side. So like some sort of and this sum is just over all other branchings for these left and right pieces. So this is going to be another important piece when we constrain these amplitudes. Okay. So there's some details here regarding if we have a theory of a single scalar or multiple scalars, or what they call flavor-ordered scalars, where the things have some sort of Lie structure or color structure, which we sort of factor out. And we'll say maybe a little bit more about that at the end. But basically, what we should think about here is amplitudes must respect permutation symmetry, where that's not really a great word because permutation symmetry implies any permutation, but really, if it's a theory of a single scalar, then swapping any leg, you need to be invariant, so you must be invariant under the whole Sn group. If it's a theory of these flavor-ordered scalars, then you need to be cyclically invariant. So those are sort of two things we must impose on these amplitudes where appropriate. Okay, for reasons of time, I'm not going to bother writing down what one of these amplitudes might look like. There are plenty of details in those references if you guys are interested. Okay, so now what I want to get to is one of the main tools we use for further constraining these amplitudes, which is the on-shell recursion relations. So basically, for Yang-Mills and gravity, you guys may have heard of the pretty famous BCFW recursion relations. And these are extremely elegant ways to extract higher order amplitudes from higher point amplitudes from lower point amplitudes, using some sort of factorization kind of structure with this and a very clever complex momenta shift. Unfortunately, for our scalar EFTs, there's no analog of gauge invariance, or sort of the BCFW shift doesn't work for our scalar effective field theories because it's not a gauge invariance that we expect to be constraining them. There is no gauge invariance. What we expect to be constraining them is their infrared dynamics. So it's this generalized Adler zero thing that we want to sort of impose on the amplitudes. And so for that, we're going to need a new way of doing this sort of on-shell recursion, which the authors here have called, I think, soft recursion. So let me introduce that briefly. Let's skip ahead. Okay. So I'm going to skip exactly what the details of the momentum shift are. I'm going to come back to those after I do this, and then just show you generally how this soft recursion works. So suppose we have a method, and I'm sorry for going out of order here, where we promote the amplitude to a function of a complex parameter z. And I will, again, show you in more detail how this works in a second. So suppose we have this, then the papers just write this down without really carefully justifying this formula, which I think they do ultimately just sort of out of order, where let me define Fn. Okay. So perhaps it was a mistake of me to go out of order here, but these AI are parameters which will be involved in the shift. This NS is the number of soft limits which are available as a result of our shift, and there will be 3 different kinds, so there will be different numbers for each kind of shift that you use. So then you can consider this expression, which is your amplitude divided by this Fn function. And the claim is it equals 0. And why do you want to say it equals 0? Well, the argument would be take your contour out to infinity. Your integrand is going to vanish there, so it must be 0. That turns out to be an interesting constraint on where these methods are applicable. And that's basically the reason that we only consider things below this line. Because being below this line corresponds exactly with this integrand actually vanishing at infinity. So these methods can actually be applied. So supposing this formula holds, then what do? We use the residue theorem. So we see that there's obviously a pole at 0, and we have 0 equals the sum of residues of this, and then there's the pole at 0. This just becomes this fn of 0 just becomes 1, and then this a of 0 is constructed such that this is exactly the amplitude you're interested in. So you want to compute a of 0, and so we have a of 0 plus the sum of over the other residues of an z over fnz, with this extra z here. And then because this equals 0, of course, the thing you're interested in is equal to the negative sum of the residues. OK, so at the risk of squeezing out things further, I'm going to just show you a little bit more about how this works, because it's pretty interesting. There are 3 possible places there could be poles in this integrand. There's one at 0, obviously. An could have a pole, or fn could have a pole, or fn could be 0. So it turns out that fn having a pole, where z goes to 1 over ai for some ai, your an is going to be constructed such that in that limit, an precisely goes like this factor. That's why we did this. So there are never any poles coming from when fn is 0. That's related to this vanishing, this limit where p becomes soft. So fn is designed to have poles where one of these particles becomes soft. When one of the particles becomes soft, we know how an behaves. And as a result, there's no poles from that. So there's just poles from an, which are the poles from, which are like the factorization poles, which are poles where some internal particle goes on shell. So you can write like sum over factorization channels an z. So I'm going to skip a couple steps. If you go through what it means for an internal particle to be on shell, you find there are 2 possible values of z corresponding to when that happens, and then the formula you get is OK, so that's how it works. You can see there's like a factorization structure and some rational function dependence, and that's basically it. OK, so that's the technique. I'm going to very quickly discuss what one of these shifts might be. Can you guys see if I go over here? Is that fine? So there's something called the all-line shift. And what you do there is you send pi to pi 1 minus z ai. And then for momentum conservation reasons, you need that. And then if you count the degrees of freedom with this shift, you find that it's applicable only when n is how many particles you're scattering in your amplitude is an n-point amplitude. When n is greater than d plus 1, so this is a rather constraining condition. This won't always happen. You'd like shifts which will work in more general conditions. So you can try the all but one line shift, and that will look similar. You will just do the same shift leaving out one of the particles. The nth particle you will shift in this way. And then you have two constraints for momentum conservation and on-shellness. Okay, so you count the degrees of freedom, you figure out when this is applicable, and you find it works for n greater than 4. And then there's one more you can do, which is all but 2. And I, for interest of time, won't say exactly what that is. I mean, it's very similar to this, you can imagine. And it works for n greater than or equal to 3, and d greater than or equal to 4. So there's sort of different regions of applicability there. Okay, so we have our recursion relations, which we're going to use. We have these different shifts, so what do we do? Let's consider the amplitude, just the contact amplitude with v scattering particles, so AV. So we know this is a contact amplitude. There's no poles, just a polynomial in z. We're considering different ones of these shifts, whichever one is applicable, and the degree of the polynomial in z. This is a z. It's poly z. So the degree is rho v minus 2 plus 2, and then sort of because because each momenta is linear in z, and it's you know how many zeros this thing has, and it has exactly vs sigma zeros, because sigma is like the power with which things vanish in the soft limit, and vs is again, I should say here n particle soft limits are available. You can take z to 1 over ai for any ai. For all but 1, obviously n minus 1 the soft limits are available. For all but 2, n minus 2 soft limits are available. So that's what this number vs is. It's just one of those. So this is the number of zeros. So you can get a simple constraint by saying the degree of your polynomial must be greater than or equal to the number of zeros that you know exist. So that looks like this. And then you can go through and consider, if d is if v is greater than d plus 1, you can use the all line shift to rule out that entire region. So one of the things you get is that v is less than or equal to d plus 1. And from this constraint, you get basically this line here. And as a result of just what I've told you, the recursion relations, these shifts, you get this line, where this line, in theory, goes up here. So what we haven't done, and I'm not going to show you, is how we put this cutoff here, or equivalently this cutoff. I'm not going to show you that. But basically, the way to sketch the argument for that is doing these shifts. Any dependence at the end of the day on these parameters ai should drop out, because those things are unphysical. You just introduce them. And if you do shifts in 2 different ways, and you still get dependence on ai, then you know that amplitude is no good, basically. So there's no amplitude that exists for that tuple of parameters. So that's a rather technical portion of the paper, but that's how they ultimately find that rho is less than 3. Or equivalently, sigma is less than 3, because there's only discrete values of sigma. Okay. Okay, let me see what I have time for. Yeah, so what's nice about V and D is you can search, when you're searching for the existence of theories, which you can do with the numerical techniques of paper 2 there, you only need to search on the line V equals D plus 1, because if a theory takes place if there are many higher dimensions, you can always imagine the kinematics of that theory happening in a V minus 1 dimensional subspace. So just by simple kinematic reasoning, which I'm not going to go through here. So if a theory can exist, you can just search for it here. And basically when you do this, you get this general region plot here, which rules out all sorts of things. And then what the authors did is they explicitly checked for v equals 4, 5, 6, or equivalently 3, 4, 5 dimensions. They explicitly checked which scalar theories could exist using, again, the numerical techniques, which I have not mentioned at all. And they found that these are all of them. So in reference 2, they found this special Galileon theory as one which no one knew previously existed, but it does live here in this regime. And so I think maybe you could just have time to circle which ones exist in which dimensions. So I think this plot is for d equals, well, it's not really for a specific d, but for v equals 4 and 5, there's just the Galileon and this, I believe. And let me see if that's right. Yeah, just these two. And this one has only cyclically ordered amplitudes, so only flavor ordered scalars. This one has both single scalar and multiple scalars. And then that's the same for v equals 6. For v equals 4, you can get these theories appearing. These theories only appear when v equals 4, and the exceptional ones. Which is interesting. They've done an exhaustive search, and we've ruled this out for these sort of interesting dimensions. For higher dimensions, higher v, you can prove again in an analogy with v equals 5 and 6. These are the only spots theories could live, but they don't have there's no proof as of yet that this Galileon theory and the WZW theory are the only ones that live there. So you could, in principle, have degenerate theories in this rho sigma space. So I think that's probably all my time, and I'm just going to stop here.